Okay, so now we're going to start Lesson 8, Parametric Equations, and this is based off of AP Unit 9. And Unit 9 really is looking at three kind of separate math subjects and how calculus applies to it. And so for our class, we'll break that down into three separate lessons, Lesson 8, Lesson 9, and Lesson 10. And so Lesson 8 is all about parametric equations. And the way that AP has this structured is that part of each topic is either refreshing your memory about that topic or maybe teaching it to you for the first time before you start to do the calculus parts to it. So this first lesson, 8-1 or 8.1, will be just an introduction to parametric equations. We'll do nothing with calculus in this lesson. We just need to understand the basics and what we need to know about them so that we can do some calculus. So here we go. Parametric equations are equations that are set in terms of a common variable called a parameter. Often parametric equations are set in terms of t for time. As a result, parametric equations allow us to model scenarios that do not have to be functions because the plane curve, which is the graph of the parametric equation, can move in any direction, including across itself. A little bit more reading. Parametric equations in terms of time have direction, but you often have a starting time and an ending time for the plane curve. Use arrows to show the direction of the plane curve. The best way to understand this is to go ahead and jump right into an example. So let's imagine that we have a parametric equation where x is set equal to t minus 2 all squared and y is set equal to 2t. So these are called parametric equations because x and y are both defined by a separate variable. In this case t, and we're going to look at t between 1 and 4. And it's often time because the real life applications of parametric equation often deal with time. So the first thing we want to do is if we want to graph the plane curve that results from the parametric equations, we want to make a table of values. And so our input is t, and we get separate outputs for x and y. So all I'm going to do is I'm going to plug 1 in for t on the x equation, then 2 in, then 3 in, then 4 in. So here we go, into the x equation, plugging 1 in, 1 minus 2 is negative 1, squared comes back to 1. Plugging 2 in, 2 minus 2 is 0, 0 squared is 0. Plug 3 in, 3 minus 2 is 1, 1 squared is back to 1. And then we're going to plug 4 in, 4 minus 2 is 2, 2 squared is 4. Okay, now let's do the same thing by plugging our t values into the y parametric equation. So here we go. Y equals 2 times 1, 2. 2 times 2, 2 times 3, 2 times 4. Okay, so we have a table of values for our parametric equation. I'm just going to kind of jump down here and make a graph of this parametric equation. Let's see, we have t. Now it's still an xy graph, so don't let that confuse you. Our x values go from 0 to 4 in different sets of numbers, and our y values go up to 8. All right, so at x is 1, we have y is 2. Let's switch that color. At x is 0, we have y is 4. At x is 1, we have y is 6. And at x is 4, we have y is 8. So it's this curve. It's part of the inverse of a quadratic. And what's important is a note that we just said here on number 3. Parametric equations in terms of time have direction. You often have a starting time and ending time for the plane curve and use arrows to show the direction of the plane curve. Well, our time went from 1 to 4. So we need to take, and our xy coordinate at 1 is our start for our plane curve. And we need to draw arrows to show the direction that it goes all the way up to 4, 8. So I'm going to go back to my parametric curve here. And 1, 2 is my start, so I'll draw an arrow. I'll just draw a couple of arrows to show that that's the direction that we go. Now this is important. This means a few things. First thing, notice this isn't a function because we have some places here where we fail the vertical line test. We have this x input of 1 gave us 2 y outputs, 2 and 6. So parametric equations are really useful for graphing things that are not functions. Okay, so there is a graph of parametric equations. And the other thing we want to think about then is we want to think about the domain of our graph. But let's actually hold off on that thought until we read and do the last thing here that we need to know to get started with parametric equations. Number 5, it says we can eliminate the parameter to convert parametric equations to what's called rectangular form. Rectangular form is just a fancy word for y equals x. So we have y and x. That's just the normal form that we're used to using in algebra. So here's how we do it. We're going to solve one of the parametric equations. It doesn't matter if we solve the x one or the y one for the parameter. So get t by itself. And you just want to choose the easiest of the two. Yes, eventually we want our final answer to be y equals. So it might be easiest if they both look great to start with the x parametric equation first. But the example I'm going to work out here with you, we're going to solve for the y one because it's easier. So then substitute what that parameter is equal to. So you'll get t equals something in terms of x or something in terms of y. Substitute it in for the same parameter into the t of the other parametric equation. And then get y by itself. And then use the sketch of the plane curve to identify any domain restrictions you have of the rectangular form. And you often have some domain restrictions because we had some time restrictions. And even if time wasn't a factor, there still might be some domain restrictions that kind of crop up whenever you take a look at the final form. So here we go. We're going to take the same two parametric equations and we're going to convert them to rectangular form. So let me copy those down. We had, well, I'll tell you what, I think we have room right here to do it. Now you can see by looking at both of these, we could solve the x parametric equation for t. That wouldn't be too impossible. But the y one's just a little bit easier. So I'm going to divide both sides by 2 and get y over 2 equals t. So now I can take that y over 2 and put it into the t of the other parametric equation. So x equals y over 2 minus 2 squared. And we do want to solve for y, so I'm going to take the square root of both sides, and we do have plus or minus x here, and we have y over 2 minus 2. Then we're going to add that 2 to the other side, 2 plus or minus x equals y over 2, and then we're going to multiply that 2 on both sides. That gives us 4 plus or minus 2 square root of x, I should have said square root a second ago, equals y. Now this is the rectangular form. But there's a big but here, big hold on a second, and that is our original time parameter was between 1 and 4, and we see in our graph here that our domain is actually greatly restricted between 1 and 4, and so what we have is well, let me get a different color going on here. We have our domain left to right is between 0 and 4. And so we need to say that whenever we go up here and we write our equations. So the domain is actually going to be between 0 and 4 on this equation. And that's the idea of converting to rectangular form. And it's an important idea. We can usually manipulate equations in rectangular form or differentiate them or do things with them that maybe we don't know how to do in parametric form. The other thing I want to say is that whenever you do convert to rectangular form, we do have that plus or minus in there. And whenever we look at our graph, we do need that plus or minus because we know that if we only looked at the positive or negative, it would be on top or bottom of this inverse of a parabola, inverse of a quadratic graph. But let's just imagine for a second that on this particular problem, our entire graph was just that part. Then we could eliminate the minus part of the plus or minus because we would only be dealing with the positive part. That didn't happen in this one, just something to look out for and be aware of. All right, great. Good luck.